y'all, today we're going to look at 7.1 on multiplying and dividing rational expressions. In this section, we're going to look at being able to simplify radical expressions and simplify complex fractions. That's going to be the last example that we do. This section kind of merges us between like the top end of Algebra 2 and the start of pre-calculus when it comes to this. And you're going to hear me talk about graphs of things. That's all pre-calculus. But I just want it in your head that this is what we're leading towards. And so for those of you taking pre-calculus as your next course, that's where we're going. So let's look at some definitions first that we need to know. Remember that a ratio of two polynomial expressions, such as like 300 over x plus 3, is called a rational expression. And remember that term rational. If you think about sets of numbers, we've talked about rational as being either numbers being rational or irrational, right? And remember that rational numbers can be written as a fraction. So let's talk about what we deal with fractions. Remember that to reduce fractions, even rational expressions, you divide the numerator and denominator by the greatest common factor. So for example, if we just had 12 over 16, we could divide both the numerator and denominator by 4 and reduce this down to 3/4. The same thing's going to happen when we have a rational expression, except we're not going to be dividing by 4, but we'll be dividing by like x plus 2. Let's see how that works in these first few examples. But remember that with fractions and with division, it's undefined when either the denominator or the divisor, what we're dividing by, is equal to 0. And so we've got to keep that in play as we look at these problems and understand that if we're going to plug in a value for x, there's going to be times that it doesn't actually work because it's undefined, because we're dividing by 0. So let's look at example 1 here. For what value is x to the 4th times x squared minus 3x equals 10, or minus 10, over 2x times x squared plus 8x minus 9? We want to know when is that undefined. Now, very quickly, we want to remember that things are undefined only when we're looking at the denominator. It has nothing to do with the numerator. I don't care about the numerator in this problem because we're just looking for when it's undefined. Now, we've got the 2x times x squared plus 8x minus 9. Now, we can do some different methods to get to these values that are going to be undefined, but the quickest is going to be factoring this. So the 2x is already factored. We can't do anything else with it. But this x squared plus 8x minus 9 is a quadratic, and we're going to use the x puzzle on it to factor it. Now, if it doesn't factor directly, of course, we could complete the square and figure things out, or we can use the quadratic formula and figure out what the zeros would be. But factoring is going to be our first go-to in a lot of these problems. So the top is negative 9 because A times C. The bottom is 8 because of the B. And what's going to multiply to negative 9 and give us a positive 8? That'll be a positive 9 and a negative 1. And so that's going to give us, when we factor this out, to x plus 9 and x minus 1. The 2x still goes out in front. And remember that we talk about the zero product property, that if I have two things multiplied together that equal to 0, at least one of them has to be 0. And so we're going to set each of these three pieces equal to 0 and solve each for x. And so we have 2x is equal to 0, so x is obviously 0. X is equal to 9, so x equals negative 9. And adding the 1, we get x is equal to positive 1. And so I have three values that this is not defined for in the domain. And that would be negative 9, 0, and 1. And so we can plug in an x value and figure out what it's going to be equal to for any value we want, except those three. All right, let's go ahead and look at example 2. In example 2, we're looking to simplify this rational expression now. Now, when we simplify it, we're looking for things that will cancel. Just like our 12 over 16, we can divide them both by 4. So in this case, we're looking for something other than just a number. We've got to factor this out and then find the common pieces. Now, one common mistake is that some of you are going to want to be like, oh, I can cancel the 2x and the 2x. You can't do that because they're not factors of this expression. And so we have to factor it out. We have to get pieces that are multiplied together that will cancel numerator and denominator. Now, to simplify this, we're going to look at the top first, and we'll have to X puzzle that. So 4 and 5, so 1 times 4 is equal to 5. And so our numerator is going to be 3x times x plus 1 times x plus 4. The denominator, the x minus 3, is not going to change because it's already factored. But the x squared minus 16 is a difference of squares. And remember that formula, if I have a squared minus b squared, that's equal to a plus b times a minus b. And so in this case, x squared, simplifying that, is going to be x for both. And 16, that's going to be 4 because the square root of 16. One's going to have a plus, one's going to have a minus. Now that we've completely factored this out, we can find common pieces that are multiplied together that will simplify and eliminate. And so we have this x plus 4 piece here and an x plus 4 piece here. That is what's going to cancel. Nothing else eliminates here, and so the final answer to simplifying this is 3x times x plus 1 over x minus 3 times x minus 4. We don't need to multiply this back in. It's actually, again, talking about the pre-calculus side of this. If we were trying to graph this up, this is going to give us information we need to be able to graph this picture in its factored form instead of being multiplied all together. Now, part B, what conditions is this expression undefined? Well, remember we talked about in the previous problem that it's undefined for anything in the denominator that's going to make it equal to 0. But that is actually before we cancel anything. So, yes, it's going to be this x minus 3 is equal to 0, and this x minus 4 is equal to 0. But it's also going to include this piece here, because it's a part of the original problem, and it's a part of the domain of this problem. And so we've got to have the x plus 4 equals 0 as well. Meaning that I'm going to get three pieces. X is equal to 3, x is equal to negative 4, x is equal to positive 4. So x cannot be equal to negative 4, positive 3, or positive 4. So again, those are the three domain values that we're looking at in this problem. All right, so sometimes we need to have the opposite signs. And so, for example, we might see 3 minus x in a problem. But in the other part of the fraction, we might have x minus 3. And so we can rewrite that 3 minus x as negative 1 times x minus 3. Now that works because when I pull out the negative, the 3 becomes negative 3, and the x becomes a positive x, and then the commutative property just allows us to switch the order. And so then we would be able to cancel. Like, for example, if I had 3 minus x over x minus 3, now we see that this and this would cancel in this problem and reduce it down. So let's see how that works in a little bit more complex problem. We've got a to the 6th b minus 5a to the 6th over 5a to the 4th minus a to the 4th b. And so again, we see here we've got an a to a power b and then a 5a to a certain power. But on the bottom, in the denominator, it's reversed. And so that negative 1 is going to allow us to reverse that order and get those signs changed so that the signs will be the same. And so doing that first, we're going to get a to the 6b minus 5a to the 6th negative 1 times a to the 4th b minus 5a to the 4th. Now, what that next step allows us to do is see that we've kind of got some common things going on. Now, nothing will just straight reduce. Like, we can't just cancel out these a to the 6th and a to the 4th and simplify it down there. Because remember, it's a piece of a factor, and we need the entire factor to be able to cancel. But watch what happens with both of these. We look up here, this and this both have an a to the 6th. And so we're able to factor that out, and what's left is b minus 5. In the denominator, something similar happens. We still got that negative 1 sitting out front, but in the denominator, we've got a to the 4th and an a to the 4th, and we factor out that a to the 4th, again leaving b minus 5. And so now we're able to cancel some things out. The b minus 5 and the b minus 5 here will cancel. And then we see that the powers here are going to reduce. They're both the base of a. And so remember, you're going to do the 6 minus the 4. And so that's going to give us a squared. We're still over negative 1. And so remember that dividing by 1 does nothing, but the negative is going to change the sign of our final answer. So our final answer is just negative a squared. So again, pay attention to things where you'll be able to switch the order and deal with that negative coming out, and also look at what common factors are being involved that might factor out to give us a common piece to be able to reduce. Okay, let's go on to example 4, and we're going to look at how to actually multiply and divide these together now. So remember that rational expressions are just fractions. And the fraction rules don't change. When we're multiplying fractions, remember that we're going to just multiply, like a times b over c times d, just straight across. So the a times the c and the b times the d. And remember that when we do division, some of you are going to give me 3 letters here, and I'm going to tell you no. Remember that you're going to multiply by the reciprocal. I know some of you want to say KCF, right? But the proper phrase is to multiply by the reciprocal. And so if I have a over b divided by c over d, remember we're going to keep that first fraction, a over b. We're going to multiply by the reciprocal of the second fraction, so that's d over c now, and we get AD over BC. And so division just changes the multiplication, and then we're able to do it like a multiplication problem. So let's look at the 2 examples that we've got here on multiplying and dividing. In example A, we've got 10x squared over 27y to the 4th times 9y squared over 16x cubed. Now, you might remember back from like 5th grade, 6th grade, where you could cross-reduce things before you multiplied out. Because, I mean, we can multiply first and reduce later, but the numbers get really big. Like, do you really want to do 27 times 16? Not really. I don't either. So we're going to reduce this first and look for common pieces. So what does 10 and 16 share in common? Well, they can both be divided by 2. And so 10 divided by 2 is 5. And 16 divided by 2 is 8. Now, we can continue this process. We look at the 9 and the 27. 9 and 27 share a 9. So 9 divided by 9 is 1. And 27 divided by 9 is 3. We can also do the same thing with our variables with powers. And remember, that's going to be subtracting powers because we're dealing with a numerator and a denominator. And so looking at the powers, we've got an x squared here and an x cubed here. So that would be looking at like this, right? We've got x times x and x times x times x for the denominator. 2 of those x's are going to cancel, leaving us with 1 x in the denominator. So this one completely cancels, and our power here goes to just 1. Same will happen to the y's. When we look at that pairing, we've got y to the 4th and y squared. So again, the 4 minus the 2 means that this power is going to go to 2, and this completely cancels. And so now we can multiply straight across, and we're basically at our final answer. And so multiplying straight across, 5 times 1 is going to give us 5. All the variables in the numerators went away. 3 times 8 is 24. We've got a y squared, and we've got an x. Now, you can leave it like this, or if you're OCD and you like alphabetical order, and that's actually the proper order to do this in, then we are going to put it as x, y squared in that denominator. But that's the final answer. Okay? So again, reduce what you can, multiply straight across, and get your final answer. And again, double check that if you need anything else to reduce, but normally if you've done everything right, you're final at that step. Okay? In example B, we see division here. And remember, with the division, we're going to first change that to do multiplying by the reciprocal. So we're going to rewrite it as 10ab squared over 3c to the 4th d times 12c squared d to the 3rd over 5a. And so I want you to pause the video here and try this example first. Think about what things are going to cancel and what your simplified answer is going to be. And you're going to be pretty surprised at how small this answer is going to get. All right, so I've simplified this down as much as we can, and you're going to see that the 10 and the 5 reduced to 2 and 1, the 12 and the 3 reduced to 4 and 1, and the variables have canceled down some as well. So let's multiply this out. And so what we're going to get is 2 times 4 is 8. The b squared is still up here, and I've got a d squared still up here. In the denominator, that's a 1 and that's a 1, so there's no number, but I do have a c squared. None of these are the same variable. There's no numbers left to reduce, and so this is my final answer. Again, when we're dealing with just monomials and we're dealing with powers and coefficients, it's pretty straightforward to simplify this. But what we're going to look at example 5 is looking at polynomials in these numerators and denominators of these rational expressions and having to think about what we've done in example 1 and example 2 on being able to reduce this. So let's go ahead and look at example 5. So here we see 2x plus 8 over x squared plus 5x plus 6 divided by x plus 4 over x squared minus x minus 6. And so when we look at these polynomials, again, we want to factor them into their smallest pieces. So again, X puzzle if we need to, or factoring out a GCF, whatever it's going to take to get this into all the little pieces so we can figure out what pieces are going to be in common. Now, first off, this is a division problem, so we need to multiply by the reciprocal and rewrite this. So we're going to get 2x plus 8 over x squared plus 5x plus 6 times x plus 4, and then, taking the reciprocal here, x squared minus x minus 6 over x plus 4. Now, look at each of these pieces. We'll start top left and work our way over. And so the 2x plus 8, we can factor out a GCF of 2, leaving us x plus 4. In the bottom left, we can do an x puzzle there. The top is 6, the bottom is 5. What multiplies to 6 and adds to 5? That's 2 times 3. And so this is going to factor to x plus 2 and x plus 3. Now, we look at the other side and we see that this will also be an x puzzle. And so we've got negative 6 and negative 1. So what's going to multiply to negative 6 and add to negative 1? That's a positive 2 and a negative 3. And so we're going to get x plus 2 times x minus 3. And this is all over x plus 4. Now we can see what pieces are going to cancel in this problem. And so when we look, we've got an x plus 4 and an x plus 4. That part will cancel. And we also see that we've got an x plus 2 and an x plus 2. That part will also cancel. Now what doesn't cancel is this x plus 3 and x minus 3. The signs are different, and there's nothing I can do to change it around or manipulate it to make it be the same. Because in this one, they both have the same sign. This, they have different signs. There's no way to get them to be the same. And so our final answer here is just multiplying our numerators back together, but not actually distributing, just writing it as multiplication. So 2 times x minus 3 over x plus 3. This would be our final answer. Now, we talked about back in example 1 and example 2 what values of x could not be valid for this, and it goes back to two different pieces here. Yes, this is a division problem, so anything in this part that makes it equal to 0 would be false, right? Because if it's 0 up in the numerator, then it's making the whole division problem divided by 0. If it's this part of it, then I'm dividing by 0 when I have the original problem, and that's an issue because I have the x plus 4 divided by 0. That would be undefined. So we've got actually a couple different places we've got to be careful, paying attention to what values are not going to take effect. Now, again, division's more strenuous than it is for multiplication, but I've got to look in all three of these areas to see what values of x do not belong. And in this case, x will not be equal to the following values. From this one, negative 2, negative 3, negative 4. We still got the negative 2 from this one, but also positive 3. So there's actually 4 numbers that we have to be concerned about -4, -3, -2, and +3. All of those are going to be issues of the domain when we go to graph these functions. Okay, we got one last example we're going to look at, and that is with complex fractions. So let's go ahead and take a look at that one. So a complex fraction is a rational expression that the numerator or the denominator is also a rational expression. Basically, it means that there's a fraction inside a fraction, right? So our numerator is a fraction, or our denominator is a fraction, or both. And so we can get some interesting looking problems like this one here, or this one here, and they look like they're difficult to solve, but they're really not. Here's the key. What operation is a fraction? It's division, people. So if I have A over B over C over D, this is division, so I can rewrite this as A over B divided by C over D. Now that's just like what we did in the previous example, right? So instead of dividing, we're going to make this what? Multiplication. Multiplying by the reciprocal, so A over B times D over C. So this problem's not as complicated as it looks. Again, when you see that fraction in a fraction, rewrite it as a division problem, and then remember, rewrite the division as a multiplication problem. So, in the example, let's take a look at this example. We've got x over 2 over 9x squared minus 4y squared, and then x over 3 over 2y minus 3x. So we've got that fraction in a fraction. And so we're going to rewrite this first as division. Now, if you are comfortable with this, you could do this in one step and write it as a multiplication. But if you're not comfortable with two steps in one here, write it out as division and then rewrite it as multiplication. So x squared over 9x squared minus 4y squared times 2y minus 3x over x cubed. Now, you're going to look at this problem and say, okay, the x's are going to cancel because there's one over here and there's one down here, but the other two look kind of weird. We'll get to those in a minute. Let's do the easy part first. So we got an x squared and x cubed. Remember, those are powers, so we're subtracting. This will cancel. The power here goes to 1. But look at this piece and this piece. Look at the variables, right? We've gone from, in the bottom left, we've got squares there. In the top right, we've just got regular. So there's a power change going on. So something's going on. And also in down here, we've got the x first and the y with the subtraction. And here the order's backwards. So I can go back and use that -1 rule that we talked about a couple of examples ago and rewrite this. So that's canceled, so there's a 1 here now. 9x squared minus 4y cubed, or squared, excuse me, times -1 times 3x minus 2y over x. So now we're a little closer. But look at this. And this is where, again, you got to go back to Unit 3 when we talked about difference of squares. This is going to factor. And so this is actually going to break up to 3x plus 2y and 3x minus 2y. So that part's been rewritten. And so now we see that this piece and this piece will cancel. And so my final answer, I've got a -1 in the numerator. I've got this 3x plus 2y, and I've got an x. So x times 3x plus 2y. So that's it. That is the section. Again, it seems like there's a lot here, but it's very repetitive once you see the pattern in these. Think about the multiplication, think about the division, think about what these fractions are actually telling you to do. So that's it for today. If you need anything, you know how to get a hold of me, and I'll catch y'all next time.